Hello friends, again welcome to this today's class. In the last lecture we have seen about the lattice, basis and unit cell and primitive unit cell, and today, yes, this was the last slide we have seen yesterday's video, and this particular thing we call it as unit cell, right? So that unit cell has some parameters and we name it as lattice parameters, that are A, B, C and alpha, beta, gamma. I told you yesterday only the A, B, C and alpha, beta, gamma are not placed randomly, they are specific, yes, and we will come to know later on what are their significance and all, but for any unit cell or for any lattice we must know these lattice parameters for further investigation, for further calculation. So today we have to see the symmetry operations. Today's lecture, today's class, today's video is based on this particular thing, symmetry operations. So what are these symmetry operations? First of all, symmetry, the word symmetry means what? Symmetry means similar to both sides. If I take the mirror image, right, so that can be called as a reflection symmetry. That means what? Whatever I am taking my image in the mirror, that image is exactly similar, but what opposite in direction, we can say. So similarly we have several symmetry operations, or in short we have anything that is symmetrical, or nature always loves symmetry, everything is symmetrical. We see the half rainbow, but half rainbow is in other part of the earth, so it doesn't mean that the rainbow is always half. So half rainbow we are seeing, but other poles people can see the remaining half rainbow. So that means what? The nature always loves symmetry. So similar, if we can take the best example of our body is symmetric along this axis, yes. If we cut this, then all the parts will be exactly similar on both the side. That is what we call symmetry. I have two hands and both hands are identical, but this is what we can say the symmetry. One is to this side, one is to this side. That is what the symmetry. Now, but this symmetry is not only related to the reflection symmetry. We have different 4 types of symmetries. Reflection symmetry, yes, obviously, but before that, first thing we will see the translational symmetry, then rotation symmetry, then reflection symmetry and inversion symmetry. Likewise, we have 4 symmetries, which are those: translation, rotation, reflection and inversion. Okay, so what are these different symmetry operations? We will see in this class. So first line on this particular slide, you can see this is a translational symmetry, and only one equation is written there: r dash is equal to r plus t. So don't worry, I am going to explain what is that r dash is equal to r plus t. If you remember the first lecture, there also we have the same equation, and for what purpose we have used it? We have used it to check the given translational vectors whether they are primitive or not, yes. So that means this r dash is a new position, r is a old position, and this t is what I told you already, t is a change, and that change contains, or that change is with the help of unit vectors u1 u2 u3 and a1 a2 a3 a1 a2 a3. We call them as translational vector. So this symmetry is translation symmetry. Now what is translational symmetry? Let us consider this lattice or the crystal initially was at point r, and by means of some operator, what we call this particular t is called translation operator. By means of translation operator, we have translated the crystal, we have translated the lattice to some new position, this r dash. So what will be the new structure, what will be the new position, what will be the new picture? And that new picture is r dash is equal to original r plus this change t. That is what we call the symmetry. And moreover, this is translation symmetry. That means what? I have translated something from one point to other point, but still the crystal remains same. That's it, simple, right? That means crystal does not have any change. Change means moreover there is no change between the two interatomic distance, there is no change for any lattice parameter, there is no change for their angles and anything else, right? Or we can say shape and size, everything remains constant. That is what we call translation symmetry. Okay, simple. If we translate from one point to another point and the crystal looks exactly same, crystal looks exactly same, we can say. Instead of going to the deeper side of the atomic level, but from the macroscopic level, we can say if we translate a particular crystal from one point to another point, crystal looks exactly same. That is called translation symmetry. Okay, now to comes to us the rotation symmetry. This symmetry is having little bit again subheadings. So the rotation symmetry means basically, yes, if I have a crystal and I want to rotate it, okay, I want to rotate it, and after rotation, at what point that crystal looks exactly same. Okay, that means let us consider I have a crystal, and that crystal I am rotating it by 90 degree, and after the rotation also it looks exactly same. So what we can say, yes, that crystal possesses rotation symmetry. Now we can take the simple example of a square. Let us consider a crystal of square structure, a crystal of square structure. Now if I rotate that square by 90 degree, again it looks exactly same, yes or no? If I rotate it by 180 degree, again it looks exactly same. If I rotate it by 270 degree, sorry, again yes, 270 degree, it looks exactly same. And if we rotate again it by 360 degree, that means again comes to the original position, it looks exactly same. So that means what, that square crystal possesses the rotation symmetry. Are you getting? Now this rotation symmetry means by how much angle you have to rotate the crystal so that it looks exactly same. Once again, by how much angle you have to rotate the crystal, by how much angle you have to rotate the crystal so that crystal exactly looks the same. That means it should possess rotation symmetry. That angle we can calculate by this formula, theta is equal to, it is 2 pi. Okay, yeah, so due to some typing error, it is not looking to something box, but that is pi. So theta is equal to, you please write down somewhere, theta is equal to 2 pi by n. Theta is equal to 2 pi by n. This formula, that formula, what is that theta and what is that n? Okay, so that n is called as n fold symmetry or n fold rotation symmetry. Okay, right? So we can read this statement once again, then I will explain. An n fold rotation symmetry means rotation through an angle of theta is equal to 2 pi by n will repeat the object or motif or crystal or lattice n times in a full 360-degree rotation, and then that time n is equal to 1 means no symmetry. Yes, what I am saying, now any crystal, any object, if we rotate it by 360-degree, it looks exactly same again. Yes or no? Anything you are rotating, and again you comes from, you starts from 0, then 90, then 180, then 270, and again it comes to 360. That means you are coming to the original position. So any object rotated by 360-degree exactly looks like whatever it was original position or however it was looking earlier. Yes or no? So in that case, that fold symmetry is known as one fold symmetry, because there is no symmetry or there is no any fold, because we came to original position. Now that n is means n fold symmetry. So likewise we can find how much fold symmetry is valid for different types of crystal. So here that theta will give you by how much degree you have to rotate particular crystal so that it will maintain the rotation symmetry. Are you getting? So one fold symmetry means simply I am rotating this particular object by 360-degree and it is coming to the original position. So that means it is also called as no symmetry or one fold symmetry, because we are not saying zero fold symmetry, because if we take n is equal to 0, then theta is equal to, it was what, anything by 0 it will be infinite. That's why we call it as one fold symmetry. And now we can put that n value in this particular equation, theta is equal to 2 pi by n. If we put n is equal to 1, what is theta? Theta is equal to 2 pi, and 2 pi means 360-degree. It means that to have one fold symmetry for any crystal, by how much angle you have to rotate the crystal? By 360-degree. So this 360 is not coming from somewhere else, it is coming from this formula, theta is equal to 2 pi by n, and I substitute this n at this point. So theta is equal to 2 pi by 1, that means theta is equal to 2 pi, that is 360-degree. Okay, now we will take again one more example, then you will understand what is one fold symmetry. So one fold rotation exists an object that requires rotation of full 360-degree to repeat itself as a rotational symmetry. That's what I told. Yes, now look at this particular object, by any angle you rotate it, it won't looks like similar. until and unless you rotate it by 360 degree. There is no another option, yes or no. If I rotate by 90 degree, it looks something else. If I rotate by 180 degree, it looks something else. If I rotate it by 270 degree, it will look something else, not exactly like this. Now if I want this structure exactly like this after some rotation, so how much rotation or how much degree you have to rotate it? Yes, there is no option, you have to rotate it by 360 degree only. That means n is equal to 1. Okay, n is equal to 1, and that's why we can say this crystal, this particular object possesses one fold symmetry. Again, now to this triangle also, it is not equilateral triangle. Okay, this is not equilateral triangle. Now this side is different, this and this sides are different. So now let us consider this was the original position, this is the original position, and I want back this position back after few rotation, after rotation by some degree of angle. Let us consider I am rotating it by 90 degree. If I rotate it by 90 degree, does it come exactly like the same? No. If I rotate by 180, no. Likewise, if and only if I rotate it by 360 degree, it won't come to the original position, or it won't looks like the original image. So that means what? Again, this crystal, if you want it in original position, it also requires to rotate by 360 degree. Right. So this is what we call one fold symmetry. One fold symmetry, that means theta is equal to 2 pi, and which implies n is equal to 1. So this formula, sometimes you know the theta, sometimes you know the n value, 2 pi remains same. So if I want to find how much fold symmetry this particular crystal does exist, then substitute the value of theta and get the value of n, right. So 360 degree, if we substitute here 360 degree, then bring this 360 to this side, this 360 and our numerator 2 pi will get cancelled, and what will be the value of n? N is equal to 1. So that means what? Sometimes you can have the n value, or sometimes you can have the theta value. From that we can bring the another value. So that is what the n fold symmetry. In general, n fold symmetry formula, theta is equal to 2 pi by n. Okay, and from that we have seen this example of one fold symmetry. Now let us move towards the two-fold symmetry, two-fold rotation axis or two-fold symmetry. If an object appears identical after a rotation of 180 degree, now this is 180 and degree, okay, don't get confused, it is not 180 or 1800, it is 180 degree, that is twice in a 360 degree rotation, then it is said to have a two-fold symmetry or two-fold rotation symmetry. Yes, because first example we have seen, to have the same position of crystal, how much angle you have to rotate? 360 degree. That what we call one fold symmetry. Yes, now for two fold symmetry, let us put the value of 2 in this particular formula. Theta is equal to, now what? Theta is equal to, we want to find, yes, we just want two fold symmetry, so we know the value of n. What is that? 2. n value is 2. Now substitute there. So theta is equal to 2 pi divided by 2, 2 get cancelled, and what is theta? Theta is equal to pi, that means what? 180 degree. That means if you want the two-fold symmetry for any crystal, so how much angle you have to rotate? By how much angle the crystal has to be rotated? It is by 180 degree. Now look at this particular structure. If I rotate this structure by 180 degree, now if I rotate it by 90 degree, it becomes exactly vertical. Okay, so it is not its original position, but one more time if I rotate by 90, that means total 180 degree, then it looks exactly same. Okay, and if again we rotate by 270, it is again becoming vertical. Again if we rotate, again it becomes horizontal, and it will be its original position. That means in one complete 360 degree rotation, how many times it is looking like the original image? 2 times. That's what we call two-fold symmetry. I hope you are getting it. Okay, and mathematically how to get that two-fold, or how to get that particular angle? Theta is equal to 2 pi by n. So n value is here 2, or in other words we can write 180 degree rotation, theta value we have substituted 2 pi divided by 180. 2 pi means what? Or 180 means pi. This pi, the numerator pi and denominator 180 get cancelled, and we get the n value will be 2. So that's why we can call it as two-fold symmetry. Yes, so this is the best example to treat the two-fold symmetry. Simply to have the similar image, how much time you have to rotate? Yes, by how much angle you have to rotate? 180 degree, and 180 degree means in complete one full circle, how many times 180 degree? 2 times. That is why two-fold symmetry. Similarly, we can have three-fold symmetry, we can have four-fold symmetry, we can have six-fold symmetry. Now see this particular example. This is the example of three-fold symmetry. Now this is equilateral triangle. Now we can have the first image. This was not the equilateral triangle, and that's why it possesses only one fold symmetry. But here we have this as a equilateral triangle. Equilateral triangle means all three sides are exactly same. Now let us consider this triangle was earlier like this, and I want the same image after some rotation. If I rotate it by how much degree? 60 degree. Now 60 degree, how to check this? Okay, three-fold symmetry. So substitute the value of n, what is that? 3. Substitute the value of n here, what is that? 3. So 2 pi divided by 3, 2 pi divided by 3. So 2 pi is what? 360, and divided by 3. So that means what? Yes, what will be the value of theta? 120 degree, 120 degree. So that means what? We have to rotate this particular equilateral triangle not by 60 degree, but by how much degree? 120 degree. And how we found that? Theta is equal to 2 pi by n. How much fold symmetry you want? Three-fold symmetry. So 2 pi divided by 3, it will be 120 degree. Likewise, this is also having three-fold symmetry. Now I have given this example very first. The square is having four-fold symmetry, because yes, in one complete 360 degree rotation, how many times it looks exactly same? 4 times. First 0, then 90, then 180, then 270, and again likewise. So that means what? This particular square structure, I want the square again exactly same. Well, it is not possible to having the 30 degree or 40 degree or even 89 degree also. It does not looks exactly a square. If and only if I have this 90 degree rotation, this square exactly looks the same. Or again you can find that theta value by using this particular formula. Theta is equal to 2 pi divided by 4. 2 pi divided by 4, that means 360 divided by 4, 360 divided by 4, that is 90 degree, and therefore theta is equal to 90. That means to have the four-fold symmetry, how much rotation angle must be needed? That is 90 degree. So this is also possessing the four-fold symmetry. Okay, and this possesses six-fold symmetry. This possesses six-fold symmetry. Six-fold symmetry means value of n will be 6. So 2 pi divided by 6, that means 360 degree. Here 360 degree divided by 6, so that is 60 degree. So for this particular hexagon, how much angle of rotation requires to get the original image? 60 degree angle of rotation. For this also we require the same angle of rotation, and therefore they possesses six-fold symmetry. But if you observe, there is no five-fold symmetry. There is no five-fold symmetry. I told about the one-fold, then two-fold, then here it is three-fold, then four-fold, and here it is six-fold. But what happens to the five-fold? Because five-fold symmetry does not exist, since this theta is equal to 2 pi by n, and that is not a complete division. 2 pi divided by n, that means 360 degree is not completely divisible, right? It is not divisible by 5. So therefore five-fold symmetry does not exist in the universe, right? So this is about the rotation symmetry. Now let's talk about the next, that is reflection or mirror symmetry. Reflection symmetry I have given you in the introduction part only. What is for understanding what is symmetry, for there only we have taken the example of reflection symmetry. So reflection symmetry is also known as mirror symmetry, because by using any mirror you can check whether this particular object possessing reflection symmetry or not. Just look into the mirror, and if you are seeing exactly identical structure of yourself, then you possesses the reflection symmetry. And if it is not there, if your hand or your some object is missing, some organ is missing in the mirror, that means you does not possesses the reflection or mirror symmetry. Jokes apart, so that means what? If you have to check the reflection symmetry, you must have some mirror type structure, and that's why it is also known as mirror symmetry. Now see, an object with a reflection symmetry will be a mirror image of itself across a plane called mirror plane. This particular vertical line, small m, it is called as mirror plane. That means yes, the object is having a mirror image, but we must have some reference point about an axis. and that axis or that particular plane is called as mirror plane. Okay, now see here, yes, I have given this example of best particular rabbit, and if I put this mirror and this looks exactly same, this particular structure looks exactly same, that means this particular organ or whatever may be the object possesses the reflection symmetry. This is also the taken one of the example, and you can take any example. That's what I am saying. Mirror symmetry is actually we are experiencing it daily. We are experiencing it daily in mirror. If you are looking into the mirror and if you are just hanging or just shaking your right hand, then you will see that yes, in the mirror you are shaking your left hand. So that is what the mirror symmetry, right? And if that shaking hand, now in real I have 5 particular fingers, and in the shaking hand if one of the finger is missing, then yes, you can say your hand does not possess the reflection symmetry, right? Now the last one is the inversion symmetry. Okay, now in the diagram also intentionally I have given this and this same object, so that you will have the clear understanding between the reflection symmetry and inversion symmetry. So here the rabbit is having its original image here and its reflection is here, but what happens, it does not have the inversion. Inversion means, now see, if this is what I am saying, this is what the image, right? This is the original particular object and this is image, and I am seeing yes, this is the mirror image. But if I am looking like this is what the inversion, and this what happens in inversion symmetry. In this operation, every part of the object is reflected through an inversion center called the center of symmetry, which is denoted as I. The object is reproduced inverted from its original position. Here yes, the object gets reflected by a plane, but in this case in this inversion symmetry, objects gets reflected, yes, objects gets reflected, but about a point, and that point is called as center of inversion or simply inversion center. That point is called as inversion center. That means yes, it becomes exactly like this, inverted, inversion. So this happens in inversion symmetry. The object is reproduced inverted from its original position. So this is for reflection symmetry, and this one is for inversion symmetry, and from the diagram only you can clearly say what exactly happens in inversion symmetry. So simply in inversion symmetry, object gets reflected but not about the plane, it gets reflected about a point, and that point is called as the inversion center or center of inversion. That's it, and it is exactly similar to the reflection symmetry in all other aspect. Okay, but why, what happens, it is taking the inversion or it is taking reflection but about one single point, not about the plane, as like in case of mirror symmetry or reflection symmetry. So this is all about the symmetry operations. So once again we will just have a look on the slides. What are 4 different symmetry operations we have seen? First one is translation symmetry. Then that translation symmetry means we will have simply if we translate a particular crystal from one point to other point, crystal looks exactly same, that is called translation symmetry. Then we have the rotation symmetry. Rotation symmetry, this formula is important, theta is equal to 2 pi by n. Yes, by mistake it is not looking pi, but that is pi, 2 pi by n, and that n is called as the n fold symmetry. Theta will give you the rotation angle by which that particular crystal can possess the rotation symmetry. But the rotation symmetry have 1 fold, 2 fold, 3 fold, not 5 fold but 6 fold, because yes, 1 fold means actually no symmetry means 1 fold symmetry. And finally then we went to the reflection symmetry, and then finally the inversion symmetry. Reflection symmetry and inversion symmetry are a little bit similar, but the inversion symmetry takes the mirror image about a point, and that point is point of inversion or center of inversion. So I hope these symmetry operations are understood to you. If you have any doubt, you can post in the comment box, and remaining things we will see in the next lecture. Thank you.